So this example shows a figure of a top view of a bar that can slide without friction. This bar is on conducting rails and it's connected to a resistor with a resistance of 6.6 ohms. The whole thing is set in a magnetic field that's directed perpendicular to the loop and into the page with a magnitude of 2.5 teslas. Calculate the applied force required to move the bar to the right at a constant speed of 2 meters per second. So we've done some things like this before. Here we're really going to pull it together with Faraday's law and Ohm's law and see what we can figure out. So what we know is going to happen is we want the bar to move to the right, so we pull on it with some applied force. It's going to move with a constant velocity of 2 meters per second. As it moves, it's going to encounter a resisted induced magnetic force. We talked about that before by looking at the nature of the forces on the charge. Let's look at it this time in light of Lenz's law and Faraday's law and see what we can figure out. So let's write down what the induced potential is. Then let's use the induced potential to find the induced current. Then let's use the induced current to find the induced magnetic force, which is going to oppose the applied force. And if it moves at a constant speed, those two have to be equal and opposite. Okay, so that's where we're going with this. Before we get started, we might ask if we know the direction of the induced magnetic field. So you hit pause and guess. So as our slider moves to the right, it's making an area with more magnetic field that points into the page. The induced magnetic field then would oppose that and come out of the page. And we can use that idea to tell us the direction of that induced current too. So, and actually, yeah, why don't we just go ahead and do this. So we move bar right. Gives more field in, which induces B out. So if our induced field is out, then the current in this part goes straight up. So it induces I, so coming around the loop this way, counterclockwise. So we can use our Lenz's law discussion to see what's the direction of that induced current. We can draw that on our loop here. So there's the induced current. So this bar is going to have a current sitting in a magnetic field, so it's going to feel a magnetic force. That's the sort of thing we discussed already. So let's write down Faraday's law. The size of the induced potential for this loop is the change in the magnetic flux with respect to time. What is the flux? The flux, so d by dt, is B times A. The magnetic field and the area are parallel. Those vectors are parallel. So B times area. We ask, what is the area? Well, if from here to here is the length, and here to here is the width, then the area is length times width. Forgot my B, length times width. Take our constants out front, B and L, dW dt, absolute value. So the induced potential is the field times the length times the change in position with respect to time. That's the speed V, BLV. So the size of the induced potential is B times L times V. If we wish, we can go ahead and put some numbers in. So the size of our induced potential is B, 2.50 teslas, times L, 1.20 meters, times the speed, 2 meters per second. And we get an induced potential of 6.0 volts. So now that we know the induced potential, we can find the size of the induced current. So V equals IR, which means that our current I is our potential, given by epsilon, divided by the resistance. 6 volts over 6.60 ohms gives us an induced current of 0.909 amps, and that flows counterclockwise around the loop. From our induced current and knowing our field, we can find our induced magnetic force. So FB, induced, is IL cross B. Everything's perpendicular, so the size of that is going to be I times L times B. Our current is 0.909 amps. The length of the wire in the field is 1.20 meters. And the size of the field is 2.50 teslas. So our induced magnetic force is 2.73 newtons. And we found the direction of that force with our right-hand rule. We know that that points to the left. So the last thing, to find the applied force, because we already found the magnetic force, to find the applied force, we know that it moves with constant speed. Constant speed means the acceleration equals 0, which means the net force equals 0, which means that the size of the induced magnetic force has to be equal to the size of the applied force, and they have to be in opposite directions. So your applied force is 2.73 newtons to the right. Okay, so we did a similar sort of problem with a different treatment before. We see that it comes together fairly nicely when you use Faraday's law and Lenz's law.